Good day, class. So this is already the second part of the techniques of integration that we have started last Monday. So last Monday, we discussed the techniques of integration that yields the logarithmic function, the exponential function, and then we also dealt with integrals in which the exponential function is having a base which is a constant. So for today, this is the second part, and this will involve what we call complex trigonometric expressions that we need to integrate. And in this case, before we do any prior integration, there's a need for us to perform what we call trigonometric transformation. So we need to transform first the original trigonometric functions that were provided. That way we can readily make use of the formulas that we have discussed so far, and even the standard formulas for the integrals of trigonometric functions. So we will start with the different complex trigonometric functions here and the corresponding trigonometric identities that you will find useful in converting them to a rather very simple form of trigonometric expression which you can integrate right away. Okay, so we have several types here of complex trigonometric functions, and under each type, we also have cases. So in the first type here, in type 1, this deals with an integral of the sine and the cosine, wherein the exponent of the sine and the cosine in the case 1 is odd and positive. So that would mean that this n that you are seeing here as an exponent is odd and it's positive. So what do you need to do if such a case arises and that you're given such an integral? You need to split the sine function or the cosine function by subtracting 1 from the exponent of the original sine or cosine function. That way, you will have a sine of n minus 1 of x and a sine of x. It's because you have here set aside the sine function which has an exponent of 1 and the rest are written before it or is being multiplied to it. This could also be done in the case of cosines. If this is a cosine function in which n is positive and odd, you can also do the splitting. Get one cosine of x and then the rest will be multiplied to that. So for example, if this is a cosine of 5 or rather cosine of x raised to 5, then that would mean that it would be now cosine of x raised to 4 times the cosine of x. You always set aside a cosine in the case of cosine of x raised to n and a sine in the case of sine of x raised to n. Now, after that, the even function sine or cosine will be converted or transformed using this particular identity, that sine squared x is equal to 1 minus cosine squared of x. Or this could be cosine squared of x is equal to 1 minus sine squared of x, coming from the very basic trigonometric identity that the sum of sine squared and cosine squared is equal to 1. So that is under case 1. Now in under case 2, if both the exponents here of the integrals that were given involving a sine and a cosine only is even, then there's a need for you to convert such functions or those functions raised to an even exponent to this particular form. So if it's sine squared of x, that would mean that you have to use the identity 1 minus cosine 2x over 2. What happens here is you double the angle in the original given sine function. So if this is sine 2x squared or sine squared 2x, this would be 1 minus cosine of 4x. The divisor of 2 is fixed. So the difference only with these identities sine squared of x and cosine squared of x is the sign that separates the 1 and the cosine of 2x here. So if it's sine squared of x, it's negative. If it's cosine squared of x, it's positive. So this is under type 1 wherein you're dealing with an integral of the sine function or the integral of the cosine function in which the exponent may either be uh, odd or even. So that's how you're going to treat such integrals here. Now, under type 2, it now involves the product of the sine and the cosine function. And under this particular type of integral, you also have two cases. So if either m or n is an odd positive integer, the other exponent is any real number. So it could be under case 1 in which these two exponents m and n are odd and positive. So if this is odd and positive, this could be any real number. If this is odd and positive, this could be any real number. That's under case 1. Now, under case 2, if both of m and n are positive, but this time even. So in case 1, it's odd. In here, it's even. What do? You also convert one particular function. Let's say this is sine squared of x and this is cosine squared of x. You convert them individually. Like the sine squared, you convert using this integral, and the cosine squared, you also convert using this integral. Then you combine the two resulting expression. What I mean with combine, if there's a product here, then you have to do expansion. You have to expand the product of these two, and correspondingly, the resulting function, which is again having an even exponent, should be using the same identity. The same principle of converting from sine squared or cosine squared to an equivalent double angle cosine. So it could be negative if it's a sine squared. It could be a positive if it's a cosine squared. Now we will go to specific examples to this later so that it would be clearer. Now, under type 3, so it's similar to type 1 wherein you're only dealing with a single trigonometric function. So it could be a tangent or it could be a cotangent. And just like case 1, it is important that the exponent in which this tangent and cotangent function is raised to is positive. So the exponent m in here that you're seeing are all or should be all positive. Why is that? That way you can split the tangent of mx into the tangent of m minus 2x tangent squared x. Meaning, from this original tangent, for example, function, you set aside a tangent squared. From this original cotangent of x raised to m, you set aside a cotangent squared. What will you do? Or what will you do with such an expression, the tangent squared and the cotangent squared? You use the identity that would lead to the second squared of x minus 1 in the case of the tangent squared of x, or you use the cotangent squared of x being equal to cosecant squared x minus 1. So I will place here an annotation. So it could be that if you have a cotangent squared here, if you're dealing with a cotangent squared of x, this would be the cosecant squared of x minus 1. The reason why, again, you set aside a tangent squared of x or a cotangent squared of x from your original tangent and cotangent functions in your integral is for you to convert this tangent squared or cotangent squared into these two identities. You may wonder, why convert the tangent squared x to cotangent squared x into these identities? It's because the remaining tangent here and the remaining cotangent here will have a derivative that is secant squared and cosecant squared. If the derivative of your trigonometric function is with it, like tangent is secant squared, cotangent is negative cosecant squared, you can readily integrate the tangent function. It's either using the formula for a basic trigonometric function or you use the power rule, depending on the remaining unit or units that you have for the tangent and the cotangent. So that's under type 3. So again, we will have the examples later. So we will have all examples discussed later. But nonetheless, that's how you deal with this type of integral. It's similar to type 1. Now, we go to the next slide. And this is type 4, or the next step, the type here. This is similar to type 2, wherein now this time, your integral consists of a product of two functions. So in the case of type 2, it's sine and cosine, a pair of the two. In here, it's tangent second squared second and cotangent cosecond. And under type 4, we have two cases again. Now, case 1 is when m is odd and n is any real number, exactly the same as that of type 2, case 1. M is any odd positive number and n is any real number. Case 2 is when n is even and positive and m is any real number. Now, in the case of case 2, wherein your n is even and positive and m is any real number, there's a need for you to split. So you need to split the second of x raised to m to second squared x times the second of x raised to m minus 2. This would mean that you have now set aside a second squared function to represent the derivative of the tangent function that was set aside in here, because what you converted is the second. If you have a pair of a tangent and a second, the same thing with if you have a pair of a cotangent and a cosecond, the second and the cosecant respectively will represent the derivative of the tangent and the cotangent. In the case of the cosecant, you only need to place a -1. So that's the purpose. Now, if you have the second squared here converted into its equivalent trigonometric identity, then that would be the tangent of x squared plus 1. If it's the cosecant, that would be the cotangent squared x plus 1. Now, any of these identities will help you later on determine what is the appropriate du for the u that you have set aside. That way, you can either use power rule or the basic integral of a trigonometric function in processing this integral that consists of a product of a tangent second and a cotangent cosecant. So that's type 4. Now, it's not yet done because we also have type 5. We can have a standalone sine integral, a standalone cosine integral. We can have a standalone tangent integral, and we can have a cotangent integral. And that's in the last 4 types that we have discussed. If we have those as standalone functions that are integrated, we can also have the second and the cosecant as standalone, meaning they are to be evaluated alone. So if the exponent of the second and the cosecant in this case is even and positive, then there's a need for you to split the corresponding second of x raised to n to second n minus 2x, or rather second of x raised to minus 2 second squared of x. This is class second squared of x. And let me annotate. So there has to be a 2 in here because it's a minus 2. So this must be your 2. Okay? And use the Pythagorean theorem to convert the second squared function here to 1 plus tangent squared. The rule is always, class, in trigonometric transformation that you have the appropriate pairing. You pair the function with its corresponding derivative. As to what identity you will use, as to what transformation you will apply, as long as it's appropriate and applicable, then you can perform the next process of integration. But the key is always transforming the original integral. That is why it's divided into these different types depending on how you will transform first the original integral to a readily integrable expression. Okay, now we go to the next. Now we have type 6. Now, this is a sign of, notice this is not anymore exponent m and n that we're talking about for the pair of the sine and the cosine. But rather, the arguments of the cosine and the sine have these particular constants appearing or being multiplied to the variable x. So this is sine of mx cosine of nx, or it could be sine of mx sine of nx, or it could be cosine of mx cosine of nx. So you have here both the sine functions having different constants multiplied to their variable in the argument, and both cosine functions having constants appearing in their arguments. But in the first one, you have a pair of the sine and the cosine. What appropriate trigonometric identity you need to use? That way this could be converted into something that you can readily integrate. So it's in here. So if you have the case of the cosine and the sine being multiplied, this is the equivalent expression for that. By the way, there should be, again, an x here. So there should be a variable x here and an x here. This also have an x. So the argument of the resulting simplified sine function or cosine function constitute of the sum or difference of the two constants that appear in the sine and cosine function, or in both the cosine and sine functions that appear in your original integral. Okay, so convert first this particular trigonometric expressions using this identity. If you have this identity now, it's just a case of a simple formula for trigonometric integrals that you will use. Because if you will integrate 1/2 sine, for example, of 10x, then that would be the cosine of 10x. Okay, the negative cosine of 10x times 20, because you will now need the 10 being multiplied in here, and you divide by 10 as well. So that would be 1/20. So just convert first this original integrals into this expression. Now, we're not yet done in terms of types because we still have type 7, I think. So let's see. Okay, so that's it. Type 6 is it. It's type 6 only. And you are, in this case, given the sign x raised to 5. So this is under type 1, a sine function. So there's a need for you to set aside. So you set aside one sine, and the rest you need to convert into cosine. So you see this? You set aside the sine, and the sine to the fourth of x is now converted into 1 minus cosine squared of x. This 1 minus cosine squared of x, class, this 1 minus cosine squared of x is actually your sine squared of x. The reason why it's being squared here, it's because it's sine of x raised to 4. Okay? Then you need to have this expanded. So if you will expand, you will have 1 minus 2 cosine squared x plus cosine to the fourth x. And notice the sine function which you have set aside here, now will represent the derivative of this cosine functions if you will evaluate the separate integrals using power rule. So you will now distribute the sine function to each of these terms after you have expanded the expression 1 minus cosine squared of x squared. So you have this, and you could see that this will just be using a simple trigonometric formula. And this one now will be having your cosine squared of x as your u raised to 2. And this is the entire sine of x dx is your du. This one is your u raised to 4. And this is your du, which allows you to evaluate the cosine using power rule. So if that is the case, the next line here would be the last line for your integral. So you could see here that the cosine was the u and its derivative is the negative sine of x dx. So set like that, and correspondingly, the answer for the first integral is negative cosine of x dx. For this one, if you use power rule, since this one is a negative, this becomes positive. So 2 cosine cube x, because you need to add 1 here, over 3. For this one, that would need again the negative. So that's negative in here. And you have cosine of x raised to 5 over 5 plus c. So after you have set aside the sine function, you convert using the identity, you expanded, and then you distributed the sine, and then evaluate the corresponding integrals with the appropriate technique. So that's how we do it in here. Okay. You will have other examples in the other slide concerning the other types. So we will need to have this erased. That way we will have a clear slide on the next example. So for example 2, this is type 2, case 2. So you have product of the cosine and the sine. And what do you need to do here, since both the exponent of the cosine and the sine are even? So if you remember, we need to use the identity. So if it's a cosine, convert it to the double angle cosine equivalent. If it's a sine, convert it to the double angle equivalent, but take note of the sign. Then have this expanded or combined, which will yield this. If you look very closely, class, if we distribute the 4 on the two terms in the numerator, the first integral has no problem, but the second one has, because this is cosine squared of 2x, wherein your cosine has an even exponent. So there's a need for you to convert it to the double angle cosine, which is this. Notice that the angle 2x now became 4x. And the 1/4 here, the 1/4 that you have here was copied in here. And the original, this one, the cosine squared of 2x in here, was converted to this identity. The 1/4 were just copied. And the same thing with the first integral. Okay? Now, the result would be now something that we need to, again, perform integration with for the last time. Now you have 1/4 dx. In this case, you will have 1/4 times 1/2. So that would be 1/8 dx negative. And in the case of the last term here, that would be 1/2 times 1/4. So 1/8 cosine of 4x. So you have that. With this, you only need to alter this part for the derivative of the u of the cosine function. So the du of that needs, if you have cosine of u du, your du must be 4 dx. So you need to multiply by 4 over 4. Okay? That way, this 4 you goes with this one. The other 4 is written outside. So which brings about this last line in our solution, which is this. So 1/4 x minus 1/8 x minus 1 over 32. 1/8 times 1/4, 1 over 32 sine of 4x. If this is combined, or if we take the difference rather of the first and the second terms in here, 1/4 minus 1/8 is 1/8 x. And the third term here becomes the second term, which is 1/32 sine of 4x. Okay, so meaning the integral of cosine squared x sine squared x dx, it has now 1/8x minus 1/32 sine of 4x plus c as its answer. Okay, that's the integral resulting from the different transformations and simplifications that we did on the original given expression. Okay, now what about this one? So under type 4, product of the tangent cube and the second raised to 5 x. So both has odd exponents. So what do? It's not outlined there in the discussion a while ago on how you deal with the product of the tangent and the second, in which both has an odd exponent. In here, what you do, you set aside a second and a tangent. So you get one tangent there, and you get second here. This is the second tangent dx. Now, if you take 1 from 3, that would be the 2. If you take 1 from 5, that would be the 4. Okay? And what you did, this tangent squared, this thing here, was converted using the identity second squared x minus 1. The purpose is for you to be able to combine later the second squared of x minus 1 with this second to the fourth, this one, the second to the fourth x. If you will expand by distributing the second to the fourth x to second squared of x minus 1, the expression resulting will need the second x tangent x dx as the du of the second, meaning you can use power rule. What do you mean by that, Miss? So this is it. So you have now this one distributed. Notice that you have now second to the sixth and second to the fourth. Okay, and then you split these two. So you have second to the x, or rather second to the 6x, then you copy the set of derivative, and then second x to the fourth, then copy the second x tangent x. It's just like what's happening here. It's like we are multiplying this one, the derivative, as a set to these two. That way we can use rather your power rule. If you look closely, if you let u as your second, then your du is second x tangent x dx. Then that will allow you to have power rule. In the case of this becomes 7/7. In the case of this, that would be 5 for the exponent over 5. So this integral has this particular answer, okay, when evaluated. So take note of that. When both the tangent and the second has odd exponent, you take away the product pair of second and tangent, and then what you do with the remaining expression is you transform them also. That way, what you will be resulting, or the resulting expression, would be a function of the second. That way now, you will just need the power rule, because for the function of the second, the derivative is second tangent, or second x tangent x. Okay, so hopefully you got the explanation on this particular example. Okay, so the pair of the second tangent product wherein both their exponents are negative. Okay, now we go to the next example. This one, under type 5. It's second to the fourth. The second has a even exponent. What do you think will be the appropriate procedure here? You can split. So let's see. We split it to 2 secant squared x, and then 1 secant squared x was converted to tangent squared x plus 1. Why do that? Why split, or why convert the secant squared of x here, this one, to tangent squared of x? Didn't you know that the secant squared of x is the derivative of the tangent? And if this is integrated, it will yield the tangent function. So if you will distribute the secant squared of x to tangent squared of x plus 1, the resulting expression will be this. This is the derivative of your tangent here, and this one can be integrated using the formula of the basic trigonometric function. So if you use power rule, so tangent of x will be your u, your du is secant squared x dx. Then this would be a simple case of power rule for the first term and a simple integral of a trigonometric function on the second term. So this is now the integral, or the answer to the integral of secant of x raised to 4 dx. Now, we have here, I have shown here showing here the different formulas that will yield the inverse trigonometric function. So this one is though very limiting because the constant that you have here should always be 1. The u squared here is the function expression. So it could be 9x squared, or it could be cosine squared x, as long as the u squared is viewed as the function. And it necessarily requires that you have it paired with the constant 1 here in the different scenarios that you have. So if you will see an expression du of the square root over the square root of 1 minus u squared, whatever this is the u here in the u squared, meaning you take the square root of that, its derivative should be complete in the numerator. It's the same thing in here if your denominator is 1 plus u squared. It's the same also whether your denominator is u square root of u squared minus 1. These three will yield this corresponding inverse trigonometric function when integrated. Primarily because if we recall our process of anti-differentiation, if we differentiate our answer here based on what you have learned last semester, it will yield this particular expression. So the derivative of the arcsine, the arctangent, and the arcsecant of u is actually equal to this. So it follows that if this answer is integrated, you will return to the original function which you have differentiated. So now in here, we will be using, or in the next examples, we will be using this integration formula. But before that class, you have to think, what if the constant that we're having here, miss, is not equal to 1? This is not equal to 1, and this is not equal to 1. If this one is not equal to 1, it's okay because you can readily place the number before the integral here, and that makes your numerator equal to 1. The problem is if this number is not 1. Do we have a formula we could use if the constant that appears here is not equal to 1? Of course, you should have a formula for you to be able to process the integral. Otherwise, this formula that you are seeing here is very limiting only for cases in which your u squared is added to or subtracted from 1. Okay, what would those formulas be? So let's proceed on the next slide. Now, if it's not 1 here, if it's not 1 here, if it's not 1 here, if it's any constant, then write that particular constant as a square of two numbers. Example, if this is a 9, then it should be 3 squared. If this is 49 or 64, this would be 8 squared. The same thing here. If this is a 25, then that should be 5 squared. Now, if you have this particular constants replacing the one in the original set of formula shown to you a while ago, we will just alter a little of the formula that was provided. So recall that the formula that you have here is just that. If you have 1 added to or subtracted from 1. If it's not, you do something with the argument of the functions that you have in the very basic integral shown to you in the previous slide. The argument u should be divided by the a, and that is the square root of the constant other than 1 that appears in the denominator of your integral. So you divide the u by the a. This u is of course, the square root of the u squared that you have here. So if this is a sine squared, then your u must be sine squared x, then your u must be sine x. Okay? And the derivative of that sine x should be in here, and that should be cosine of x dx for us to be able to write this particular answer. In the case of the arctangent, there's a need for you to divide by the constant, which is equivalent to the square root of the constant added to u squared. And that's the same thing with the arcsecond. Okay? This inverse trigonometric function arcsecond yielded from this particular integral. What does this particular 2 bars mean? Your u has to have an absolute value, which is, of course, at all times should be positive. If you are processing this integral later on and the u, example lang, the u has a negative value, what you will substitute here will be the positive value of the root. When will that case be? When the limits that are provided here in your integral are negative. So what you will place here is the absolute value of that. Now, you will know about evaluation of integrals, definite integrals which has limits sometime in midterm before we go to applications. Okay, towards the end of midterm or before end term before we go to applications. Okay, now, this is actually a different process now, different from the trigonometric transformation. But still, it's dealing with complex trigonometric functions. Either the trigonometric function is part of the integral or that particular trigonometric function is the answer to a particular integral. In this case, these are your integrals. So we're still talking about complicated integrals, which has the trigonometric and inverse trigonometric function. Okay, so as an example to integrals yielding the inverse trigonometric function, you have here this one. So you have 1 all over the square root of 9 minus 4x squared. Okay, we'll make this bigger. Now, this your u, this is actually your a squared and this is your u squared. So your a squared is 9, it follows that your a is 3. If this is your u squared, then your u must be 2x because 2x squared is 2x rather is 4x. If you will differentiate 2x, that would be 2 dx. Okay, so if this is a squared and this is u squared, the derivative of the u should be complete in the numerator. So you see this 2, it was introduced here and there's a need for us to place 1/2 before our integral. Now, this particular form is comparable to the arcsine function yielded by an integral. So you have the arcsine of u over a. Our u is 2x, our a is 3. And of course, you need not forget the 1/2 that you have set aside in here. So 1/2 the arcsine of u over a. Now, in this case, class, if we go back to our previous slide, there must be something missing here. This is the arcsine. Now, if you recall, or I'd rather go back to that particular slide, but I will not erase what I have written here. If you recall in the previous slide, when do you place the 1 over a? The 1 over a only appears in the arctangent and the arcsecant. So don't forget that for the arcsine, we don't have the 1 over a. So then what we have here is correct. There's no need for us to write a 1/3 to be multiplied to 1/2 because we're dealing with the arcsine. If it's an arctangent and an arcsecant, there's a need for us to multiply by 1 over a. In this case, that would be 1/3. Okay? So that's it. So this one is an example of an integral yielding an inverse trigonometric function. Okay, we go to the next example. This is still pretty much like thinking that we're still talking about an integral yielding an inverse trigonometric function. So in this case, your u is e raised to x. So in this case, this is your a squared and this is your u squared. Then if this is your u squared, your u is just e raised to x. If you differentiate that, that would be e raised to x dx. And it's here. It's complete because our formula dictates that this should be a squared minus u squared du. So we didn't have any problem because the du is complete. Now this one need not be a perfect square root. As you can see, a here is square root of 5. Okay? Now, this would be yielding, so this is a constant minus a function that is being squared. So what do you think will be the corresponding integral for this? It would still be the arcsine. Notice the u that was placed here is e raised to x. The a is square root of 5. And we don't have a 1 over square root of 5 here because we don't have that for the arcsine function. We only have that for the arctangent and the arcsecant function. Okay? Now, what about this second example? Okay, let me just erase this. Okay, you have x squared and you have 25 plus x raised to 6 in the denominator. So this will be now not included under the radical sign, or your denominator is not a radical expression. So you have a squared, you have u squared. This should be du. Okay? So if your u squared is x to the 6, then your u must be x cubed. Its derivative is 3x squared dx, which means that this one needs a 3. So you place a 3 here and you place 1/3 here, or equivalent to multiplying by 3 over 3. Your a is now a perfect square. So it's 5, or rather your a is a perfect number. It's not a number which is a decimal because you're dealing with a perfect square, which is 25. Now, if we proceed, this is very simple. You have that 1/3, the one that I have written there, and your answer is 1/3. So you have 1/3. But take note that we're adding the square of two expressions, a constant and a function of x. So then that would be yielding the arctan of u over a. U being x cubed and a being 5. But don't forget that in the case of the arctan, there's a need for us now to multiply by 1 over a. So your 1/3 times 1/5 would be 1 over 15, the arctan of x cubed over 5. See that? So this one now yields an arctan function, because the denominator is not in the form of a radical expression. Okay, now we proceed with the next part here. Now, number 4. Whenever you see an expression written before the square root sign, then you will right away think that's a second or an arcsecond. So if that is the case, we'll check if everything is doable in terms of an integrand yielding an arcsecond. Again, this is your a squared. Sorry. This is your a squared and this is your u squared. and this is your a, should be your a. And sorry, is that correct? I'm so used to writing the constant before and the variable after, but in the case of second class, it's the other way around. It's the variable followed by the, so I have here, okay, it's the variable followed by the, this is your u squared, this is your a squared, and this is your u, supposed to be your u, okay? And the numerator should be your du. Okay, so if your u is 2x, your u squared is 4x squared. So we take the square root of 4x squared, and that's 2x. The derivative is 2dx. So we need a 2 here, and we need a 1/2 here to complete the derivative. And your a is 6. The way it is written, actually, it's already a standard form of an integral that will yield an arcsecond. But this one has to be a u. So what will be done there is very simple. You just need the u that you need, and that's the 2x. So in that case, you will have here, this is 2, you have 2, so you have, take out 1/4. Why is it 1/4? Okay, so we can set aside the 1/4 and leave the x here. So you'll be placing the 2 and the 2x in here. So it's the same thing. What was set aside here is the constant 1/4. It was placed outside. The 2 was placed in here, so that would now be representing the u from the u squared, which is 4x squared. It's still the same. So you multiplied by, in this case, you need not multiply by 3/3. So there's an error here. I was not able to erase. So this one should not be in here. Okay. They should be taken out. There's no need for us to multiply by 3/3. This may be caused by my copy paste thing. Okay, so there's no need for a 3/3. So your answer for this integral would be a 1/4, which you have set aside 1/a, the arcsecond of u over a. The 1/4 times 1/6 from the 1/a arcsecond of u, which is 2x, over a, which is 6. So that would be 1/24 arcsecond of 2x over 6. So this one should not be there. So there's no need for you to multiply by 3/3, but rather you multiply by 2/2. Anyway, it's already presented in here to complete the derivative of your du. Okay? Now, this is the last part of the slide. I know you have a lot already in your plate, but there's a need for us to hurry up. That way we can finish the vast topic for midterm that we need to um, tackle. Okay? Now, when you are dealing with an expression which constitutes of functions that are not similar but they are multiplied. What do I mean? X is not similar to sine x. X is just a variable and sine of x is a trigonometric function. In cases wherein you have a product of two different functions, it could be exponential and trigonometric, or it could be exponential and algebraic, there's a need for you to use the integration by parts technique. And this is the last part. The need here for this method is for you to be able to uh, shall I say, intelligently determine what's the appropriate u in your expression and what's your dv in that expression. Let's take, for example, the very simple integral here, which is x sine of x dx. When you choose your u, it should be a u which will not yield a derivative that is complicated. Normally, that's what I tell my students. So when you choose your u, it should be a function in which the derivative will not be too complicated. So let's say your u is x. So this is your u. it follows that the entire expression that you are seeing here is the dv. That is why you see here the dv is sine of x dx and your u is x. The next thing you do for the u, you differentiate. So u is differentiated and the dv is integrated. So they are opposite. Now you have u being differentiated. So x when differentiated is dx. dv being integrated to yield the negative cosine x. Then you follow the formula here that the integral of u dv is equal to uv minus the integral of v du. So whenever you use the integration by parts techniques class, it is expected all the time that you will have two terms resulting from one particular integral. So in this case, if we will process using the integration by parts, you will have uv, so u times the v. So negative x cosine x minus, this minus integral of v du. V du, negative cosine of x dx. So actually this is a cosine and the integral will be a sine. So in here you did differentiation, in here you did integration. The last part will only need you to integrate the second term from the formula that was used. And that's just the sine of x. That's it. You use integration by parts for the product of these two different functions, the integral of two different functions. Okay? Now, here is another example. You have an x and an ln, x squared dx. Now, I said you will choose the function most of the time that is simplest to differentiate. Now, this particular example illustrates the exception to that particular suggestion. Why is that? If you make your x as your u, the du will be a dx. That means that this ln of x squared dx will be your dv. But recall class that your dv must be integrated. Now, if you stick to the rule that the simplest variable should be differentiated, you cannot integrate the ln of x squared dx. Stand alone as it is, it cannot be integrated. So we will make an exception in this case. So you have to make the ln of x squared as your u and the x dx as your du. So I will have to have this one as u and this two as du. dv rather. It's dv. Okay? u and dv. If you have u as ln of x squared, then you will have, let's place here, u is equal to ln of x squared. If you use the property of logarithm in EMA 101, this could be written as 2 ln of x. The exponent here could be written before the ln, just like what's written here. And you can differentiate this as 2 ln of u is du. The u here is differentiated, which is dx over u. So this is your u in this case. U is 2, your u is ln of x squared, and this is it. The du, this second line, is 2 dx over x. If you will stick to this original process of having the u represented by ln of x squared and x dx as your dv, if this one is integrated class, the x dx, that would simply be an x squared over 2. If you use the uv minus v du process, the resulting expression that you will have on top is, so you have u and the v. So my u is 2 ln of x and the v, which is x squared over 2. This is my v and this is my u minus the integral of v, which is x squared over 2 v du, which is dx over x. So uv, u 2 ln of x times uv, x squared over 2, and then you have integral of v. The v is x squared over 2, du is 2, sorry, it has a 2 dx over x. In this case, your du is 2 dx over x. So we cancel this. We cancel this. We cancel this. Yielding an expression which is, it's suggested that whenever you have an ln, you write products of it before the ln. That way it will not be misunderstood as part of the argument. The x squared is part of the argument of the ln. Minus the integral of this x squared over x is x dx. This will give an answer which is x squared ln of x minus x squared over 2 plus c. Let's see if the manner in which it's presented in here on the slide will yield the same answer, because in here it was already, I'm referring to the ln of x squared, it was already simplified. Let's see. So you differentiated here, you integrated here, and this is your answer. X squared ln of x minus x squared over 2 plus c. So it's the same thing. Whether you do the simplifying before, just like in here, or after, you will still be yielding the same answer. So I'd like to erase what I have written in here. That way you will see things clearer. Now you already converted the ln of x squared to 2 ln of x. And this is your u, the du, the dv, and the v. You did differentiation and integration. This would still be your answer. Exactly the same as the method that I have shown a while ago. So that's in the case of the second example for integration by parts. Okay, now we go to the next. Okay, I think this is the last part. You have u here set to be x squared. The du of that is of course 2x dx. The dv is cosine of 2x dx. The v is 1/2 sine of 2x, because there's a need for us to place a 2 here and a 1/2 here. That way we can integrate the cosine, the sine of 2x. Then we use the formula uv minus v du. So uv, u and v, so 1/2 sine of 2x, and the x squared minus the integral of v, 1/2 sine of 2x du, 2x dx. Now these two will cancel each other, so you will have 1/2 x squared sine of 2x, leaving you with this particular integral. Now, this particular example was really chosen because you are not only doing integration by parts once here, but rather twice. This cannot be integrated by itself. So there's a need for us to set a new u and another du. So your u is x, your du is dx, your dv is the sine of 2x dx, and your v is negative 1/2 cosine of 2x. So in the process class, the second integral here will be replaced by another uv minus v du coming from this second set of uv and v du. So you have now 1/2 x squared sine of 2x minus, so you will have now v negative 1/2 cosine of 2x times x u, plus, because it's a minus the integral, but it's minus, so plus 1/2 the cosine of 2x dx. This now can be integrated. Now we copy the first term, we copy this one, turning it to positive, and we evaluate this. So a cosine will yield a sine provided that you have a 2 here. So this would be 1/4. This is negative, so this is negative. So 1/4 the sine of 2x plus C. You will encounter a lot of these cases, not only here in integral calculus, but even in differential equations, and even later on in the case of the chemical engineering students in your chemical reaction kinetics. It's not at all times that you will only integrate by parts once. Sometimes it happens twice. In this case, you did integration by parts twice, but you still follow the same principle. Select a U, get the du, select the dv, and perform integration to get the v. And then follow the formula, uv minus the integral of v du. Okay, this one is a little complicated, and I think this is the last part, the last example under integration by parts. So you have e raised to x times the quantity 1 plus tangent x secant of x dx. Now, we can write this as a distribute the secant of x to this part here. So you have e raised to x secant of x dx, and also secant of x distributed in here together with the e raised to x. Okay, you have that. Now, we select the simplest expression to differentiate. In this case, at times class, you will not know right away what function is u and what function and what should be the dv. Sometimes it's a trial and error thing. So if we select the second, the du is the secant of x tangent of x dx. So if you select the secant of x here as your u, the du is secant of x dx. If the dv is e raised to x dx, then your v would simply be e raised to x. Now, what will happen? Let's look at this. So you have the integral of e raised to x secant of x dx. Yes, and then you have this one. For this integral, you have tangent of x secant of x dx is your du. This would be it. And then this is your vuv. Okay. This particular integral that is written should be this integral class. So there's an error again in here due to several copy paste, I guess. So this one. This integral is e to the x tangent of x secant of x dx. You use integration by parts in here. Okay. You did integration by parts first in here. The reason why the u was selected to be secant of x so that your du will be this remaining expression here. Okay, tangent of x secant of x. The dv is e raised to x dx, and it will yield this one. Now look, if this is the integral in which we perform the integration by parts, the original integral, which I will not copy anymore, will be equal to the integral of e raised to x secant of x dx plus this. So plus e raised to x secant of x minus e raised to x tangent of x secant of x dx. This one. I copied this. So this is the e raised to x secant of x dx. This one was copied, but that one is already the answer. And you have this particular integral. You have this. Okay? It's still an integral. Now what will happen to this one? Okay, we'll see here. We go to the next part. I'll erase first the things that are clear first. Okay? So what you will have now will be this one. So this entire thing is e raised to x secant of x minus this one plus the integral of e raised to tangent x secant of x dx. Wait, class. If this is distributed, you have e raised to x. I made the mistake, I think, in this part. Because if this is the entire integral and it's written like this, you have this one and you have this one, but this one is still an integral in itself, not that you have this. So I will redo this part, class. I will redo this part because there's something wrong here. Probably too sleepy already to edit. Okay, I will redo this part on Monday, in which I will present more examples on this set of slide alone because there's too many in here. Okay, on Monday we will have more examples on the topics that we have discussed this week, and on Wednesday will be your quiz for the topics that have been discussed already. So we will polish this one and we will have more examples specifically um, focused on this particular recorded lecture. That way you will get used to having several topics known already, and then just a particular integral will be picked from that particular topic, and you will readily know how to deal with it or how to evaluate the said integral. So I will stop for now in here and finish everything by Monday. I will have this edited, this portion edited, and will share the edited portion to you on Monday. Okay? Hopefully you learn something out of listening to this slide. I see you, class, on Monday, or let's hear each other again from on Monday.